Welcome back. In the previous video, we took apart the head and the tiller assembly of that Haswing Protruar 2.0 24V electric trolling motor. We also did a lot of measurements, reverse engineering the electronics inside here, with a focus on the throttle control. Card here, link in the description. But you know how it is. The more you learn, the more questions you got. So in this video, I want to do some more measurements around the throttle control, and in addition, I want to do some measurements in regards to the buzzer. Enjoy! Last time we did all our measurements directly manipulating here the throttle potentiometer. And my concern is that we lost some information doing it that way, because when the whole thing is fully assembled, some mechanical constraints might also apply to its rotation. For example, the throttle has a defined zero position, which is implemented via a little indent here on the shaft and a spring. Also, we have 15 markers here for forward, but only 9 markers for reverse. And in the previous video, because of that asymmetry, I suspected that the potentiometer might be logarithmic, but maybe that's not the case. Maybe that's done by the mechanics. We'll find out. So, let's reassemble the tiller. The tiller and the throttle potentiometer fit only together in a very specific way, because we have 1, 2, 3 notches here. Yeah, at the top there is no notch. And we have 1, 2, 3 notches here on the head of the potentiometer. So no problems there. So all we have to do is stick the potentiometer in here so it fits after some rotation, and then reinsert the whole thing here, making sure that the glands here are aligned like that. And it should, whoops, yeah, you heard that maybe, snapped into the zero position, and now I'm reinserting the screws. Remember, Phillips size 2 and self-tapping. So I'm going counterclockwise first until I find the start of the thread. That was not good. And the other side, finding the start of the thread. Sorry for that. I got now some of the grease on my hands, so everything is a little bit slippery. Finding the start of the thread, there it is. Not over torquing it, because it's all plastic and self-tapping. Okay. Works almost. Now we attach the upper shell. Here we go. And now we have to insert, I think, 4 more screws from the bottom. So, 4 times. Finding the start of the thread. And torquing everything down. Perfect. Now we will measure the current coming out of the throttle via the yellow wire and going into the motor controller throttle input by inserting an amperemeter here. At the same time, we will measure the voltage between the motor controller throttle input and the black wire that is our 0 volt rail. And we do that after the ampere meter because there might be a non-negligible voltage drop across it, because we are measuring in the microamp range. In addition, we will also measure the power consumed by the motor. Here's our measurement setup. A bit chaotic, I know. Anyway, the yellow wire from the throttle wiper goes into that red probe and wire that red cable to the ammeter, and the ammeter returns via a black wire off screen, and that black probe into the yellow wire, the throttle input of the motor controller. That red probe here is only holding together the red wires of our 5-volt rail, and that black probe here is holding together the black wires of our 0-volt rail, and that leads also via a black cable to our voltmeter. And here are the multimeters. That was the red wire from the wiper going into the ammeter in the microamp range. And here is the black return wire to the yellow wire of the motor controller input. At the same time, we're taking here the positive voltage and link that over here to the input of our voltmeter. And that black cable is our reference to the 0-volt rail. We will do the measurements for the 0 position and then for every single marker forward and reverse. Let's get cracking then and power that thing up. Wonderful. I won't read out all the measurements, okay? I will just go through it, and then I'll present you with a table at the end. So, first marker, nothing happens, we are forward. Second marker, nothing happens. Third marker, motor starts. Fourth marker, fifth, sixth, seventh, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so the last few markers, nothing happened really. Let's go back to 0 and go into reverse. First marker, okay, already something happening. Second marker. Third marker, fourth marker, fifth marker, sixth marker, seventh marker, eighth marker, ninth marker. Okay, I will review the footage now and then I'll present you the table and maybe we can learn something more. Here's the table I promised with all the measurements we did. The first column here is the marker at which we took the respective measurements, and the reverse markers are negative. The second column is the throttle, so the throttle voltage we measured, and I inserted here 2 more data points from the previous video. That is the minimum voltage and the maximum voltage where the motor is still stopped. I extrapolated the markers for these voltages because they are somewhere in between. If we plot the throttle voltage against the marker, we see that the voltage changes in a linear fashion with the rotation of the potentiometer. So it's not a logarithmic potentiometer as I theorized in the previous video. However, at the end of the rotation range of the potentiometer, the voltage, that is the resistance, stays constant. That's a little bit unusual, and it's probably done this way to account for tolerances, so we can really be sure that when we go to one end or the other end, that we are really getting the maximum power out of our motor. We also measured the throttle current, so I throttle, the motor current, I motor, and the motor power, P motor. I also expressed the motor current and the motor power as percentages of the maximum values we measured at the markers 12, 13, 14 and 15. That would be 1.764 amps and 42.334 watts. I manually set the values here to 0, where the motor was not turning at all. And again, in reverse, I assigned negative values. Of course, the values in both columns are identical because we operated that motor at a constant voltage of 24 volts, and power is just those 24 volts times the current. If we plot the motor power against the throttle voltage, we get that graph here, which has 5 distinctive zones. First, we have here the dead zone where the motor is not turning at all, so 0%. And this is quite large, again, to account for tolerances and make sure that if we move to marker 0, the motor is really stopped. The whole thing is a little bit offset from the center voltage of 2.5 volts, which made me suspect in the previous video that we have a logarithmic potentiometer, which is not the case. It's linear. Second, we have that, approximately linear zone here where the motor power increases linear with the throttle voltage. Third, we have another linear zone here for reverse, so negative values, where the motor power also increases in a linear fashion with the throttle voltage. Fourth, we have here at the end of our forward range a little zone where the power increase to the motor peters out a little bit even when we increase the throttle voltage. Please note that this last data point is actually 4 data points in our table. And finally, fifth, we have here exactly the same effect at the end of the reverse range. And here you can actually see that the last data point here in the graph is several data points in our table. The reason being, while the throttle voltage here in the reverse range for the last 3 data points didn't change, I got here slightly fluctuating readings for the motor current and power. I didn't get that here because when the throttle voltage stopped changing, I just copy and pasted that lines in the Excel. Yeah, my fault. 2 more remarks. First, in the reverse range, we not quite reach 100% of the power we reach in the forward range. It's only about 85% or so. Second, in forward mode, the motor power changes much slower with the throttle voltage than in reverse mode, meaning in reverse we have less control. I also calculated the input impedance of the motor controller for the throttle signal by simply dividing the throttle voltage by the throttle current. And as you can see, it's pretty much 100 kilo ohms, which I correctly suspected in the previous video. Before we move on to the buzzer, I want to measure how much the motor current is fluctuating and at which frequencies. You might have noticed while we took the measurements that the current and the power displayed by my power supply were fluctuating quite a bit. And if we decide at some point to measure the current ourselves, we need to characterize that noise so we can filter it out. So I inserted a 100 milliohm resistor between the positive binding post of my power supply and the red battery cable of my motor. And across it I connected an oscilloscope probe. Let's do some measurements now. I have the probe AC coupled and we have the bandwidth limit in 20 megahertz. And already, without the motor even running, we are measuring here a noise level of about 100 millivolts. That's quite a lot, but then we have quite long battery cables connected to the whole thing. The motor is now running at its lowest setting, and I adjusted the vertical scale and the time scale so we get a clear picture of the signal. Now, let me stop the sampling and adjust the cursor, and then we read out some values. Let's first have a look at the frequency. So I set my time cursors to capture 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oscillations. And it says here aboutish 15 Hertz. So 15 Hertz times 10 is 150 Hertz. Then I tried here with the vertical cursors to capture the valleys and the tops of the oscillation. And it says here, when I measure here at the top, 95 millivolts. However, if I measure here at the bottom, the valleys and peaks, I only got about 50 millivolts. The motor is now running at full power. Let me stop the sampling and switch off the motor again because it's really noisy. Okay, give me a second to adjust the cursors. So, frequency is simple again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oscillations give us 87 Hertz, so 870 Hertz. And when I measure here, I took that center section here, the amplitude, that's about 70 millivolts. Now let's try the same at the bottom. Yeah, at the bottom, you could call that also 70 millivolts. So, with the oscilloscope and a 100 milliohm shunt AC coupled, we measured with the motor off a noise of 100 millivolts peak to peak. And at the minimum motor setting, we measured at the top of the waveform 95 millivolts peak to peak, and at the bottom 50 millivolts peak to peak at a frequency of 150 Hertz. With maximum motor settings, we measured 70 millivolts peak to peak, top and bottom of the waveform, and a frequency of 870 Hertz. If we divide for the minimum motor setting our 95 millivolts by our 100 milliohm shunt, we get a current fluctuation of 0.95 amps peak to peak. That is questionable, because we only measured half an amp total current consumption at that setting. The 50 millivolt peak to peak divided by the 100 milliohms gives us exactly half an amp peak to peak. That's at least possible, but yeah, it's all very noisy. Then for the maximum setting, we measured 70 millivolts peak to peak at the top and bottom of the signal divided by 100 milliohms. That gives us 0.7 amps peak to peak. And for the maximum setting, we measured before a total current of 1.764 amps. So that's possible. I still don't like these measurements because they were far too noisy. So let's try something else. So let's try something different. I removed the shunt resistor and instead looped in my multimeter as an ampere meter. The nice thing about that multimeter is it has different AC/DC measuring modes for current. The motor is on its minimum setting now, And we are here in combined AC-DC mode, effective of course, measuring about 360 milliamps with an AC component, effective of course, of 20 milliamps. Let's switch that to AC and Hertz, and there we basically measure nothing. Okay, next mode would be DC only, yeah, 360 milliamps. And then we have a DC only with the AC component, yeah, 360 milliamps, 20 milliamps AC component. That's not too bad, is it? Now let's go to full power. Now we're at full power, combined AC-DC, 1.8 amps, AC component, 290 milliamps, AC only, 280 milliamps, and it can't measure the frequency, it's probably too high. DC only, yeah, 1.7 milliamps. And DC 1.7 milliamps with an AC component overlaid of 280 milliamps. With the multimeter, we measured at minimum motor settings a current of 360 milliamps with an AC component of 20 milliamps effective. At maximum motor settings, we measured a current between 1.8, 1.7 amps with an AC component between 0.28 and 0.29 amps effective. If we convert the 20 milliamp effective AC component we measured for the minimum motor setting into a peak-to-peak value, we get 57 milliamps peak-to-peak, which is a far cry from what we measured with the oscilloscope for the minimum motor setting. By the way, those 57 milliamps peak-to-peak are about 16% of the total current of 360 milliamps we measured. If we do the same for the maximum power setting, we get 0.82 amps peak-to-peak, respectively 0.79 amps peak-to-peak, which is not that far away from the 0.7 amps peak-to-peak we measured with the oscilloscope. So it seems that for minimum power settings, the whole thing was simply too noisy. And these 0.82 amps peak-to-peak, respectively 0.79 amps peak-to-peak, are equivalent of 45%, respectively 46% of the total current we measured. So yeah, our power rail is indeed quite noisy. But now let's finally move on to the buzzer, and we first start by measuring the resistance. And we got here, oh, that's fluctuating quite a bit. Now it's stable, 4.6 mega ohms. And if we reverse the polarity, we got nothing at all. Now let's measure the current through the green wire. Okay, I think I go into crest mode again. Okay, 27.3 milliamps. That's not nothing. Do we have a minimum? Oh, yeah, Next, let's measure the voltage between the red wire, that is our 5-volt rail, that's also connected to the buzzer, and the green wires of the buzzer. That's of course fluctuating wildly, so let's go to crest mode. It says 4.65, let's say 4.7 volts. And the minimum, oh, there we also have a little something. That's probably just a little overshoot from the high frequencies here. I mean, these are audio frequencies. Just to be on the safe side, let's have a look at the scope too. I'm measuring here again the voltage. This is just 50 Hertz noise. And now let it beep. Okay. Stop sampling and we can do some measurements. We got a frequency of about 2.45 kilohertz. And here the maximum voltage is 5.04 volts. And these lowest peaks here, at least what the oscilloscope sees, is at 2.14 volts. So yeah, there's also too much stray inductance and capacitance in the whole setup to get a clear picture. Now I inserted a 10 ohm shunt into the green wire and we're measuring the voltage across that shunt, so everything's off. That's the noise at 0 amps. And let's make it beep. Okay. I'll adjust the cursors. We're still, of course, measuring a frequency here of 2.46 kilohertz. And we're measuring here a voltage across our 10 ohm shunt of 500 millivolts. So 50 milliamps. We've measured an input resistance of that buzzer with a positive here and negative here of 4.6 mega ohms. The other way around, we had open circuit. With the multimeter, we measured a maximum voltage of 4.87 volts and a minimum voltage of minus 0.16 volts. That's probably just an overshoot. With the oscilloscope, we measured a maximum voltage of 5.04 volts. So both maximum voltages are quite close to our red 5 volt rail. Now with the multimeter, we measured here a maximum current of 27.3 milliamps and a minimum current of minus 4.7 milliamps. That's again probably only an overshoot, because with the oscilloscope we measured a maximum current of 50 milliamps and a minimum current of 0 milliamps. And that's all at a 2.5 kilohertz square wave. But what does that all mean? It means that we have here a piezo transducer that is switched inside the motor controller to the 0 volt rail, either via a bipolar open collector circuit or a MOSFET open drain circuit. Though it might also be possible this is just a totem pole output of the microcontroller. So, what did we learn in the previous video and this one? 24 volt nominal comes in through the battery connectors via an 8 square millimeter American wire gauge 8 cable. And there is immediately a branch off to the battery indicator. Note, we have high sinusoidal current fluctuations here on the power input, between 150 Hz and 870 Hz. For example, 0.8 amps peak to peak when we are drawing 1.8 amps. Then the whole thing continues here inside with 6 square millimeter cables, American wire gauge 9, into the motor controller. Out of the motor controller, we got a 0 volt rail, a 5 volt rail, and we got also a throttle input with an input impedance of 100K. The throttle assembly itself consists of a 10K linear potentiometer, which wiper is connected to the throttle input. Each sides of the potentiometer are connected via 1K resistors to the 0 volt rail and the 5 volt rail. The voltage at the throttle input measured relatively to the 0 volt rail is as follows. If the throttle is centered, not though the potentiometer, we have 1.58 volts and the motor is off. The motor stays off in a voltage band between 1.40 volts and 2.04 volts. If we increase the voltage further to 4.55 volts, we ramp up the motor power in a linear fashion to 100%. We can further increase the voltage to 4.59 volts, but the motor still stays, of course, at 100%. If we decrease the voltage from 1.40 volts to 0.52 volts, the motor goes into reverse and increases in a linear fashion its power to 90%. And if we decrease further the voltage to 0.40 volts, the motor still stays in reverse at 90% power. The piezo buzzer works at 2.5 kHz and is connected to the 5 volt rail and the buzzer output of the motor controller. It should draw no more than 20 milliamps. I'm conservative here. We measured 25 milliamps, respectively 50 milliamps with the multimeter, respectively oscilloscope. Internally, this is probably just an open collector, open drain circuit connecting the buzzer output to the 0 volt rail. Though we measure almost 0 volts, that is 0.6 millivolts, between battery minus and the 0 volt rail, respectively 24 volts nominal between battery plus and the 0 volt rail, there is no direct connection between battery minus and the 0 volt rail. So never connect battery minus and the 0 volt rail. And that's it. And also, that's it for today. I think we know now enough about the internals of that thing to design our own throttle control, an electronic one, which we'll start with in the next video. Till then, bye!